Hello everybody, welcome back to my channel. I am Zach Peterson. Today I'm here to talk to you all about your most burning questions about PCB design. And today we're going to be talking about a question I received on one of my videos on the Altium Academy channel, and that question is all about coplanar transmission lines. Let's jump in and get started. So before we get started looking at some example designs, let's take a look at that viewer question. KP6137 writes, "Hi Zach, can you make a video to talk about and explain which layout is considered coplanar configuration, which layout is considered a non-coplanar configuration?" All right, this is a great question, and it relates to the placement of ground around the traces and components on the surface layers of a PCB. So typically when we say coplanar ground, we're talking about ground that is placed as copper pour around all of your signal lines and around all of your components on your top and your bottom layers. Now, you can also have coplanar ground on internal layers, but of course that coplanar ground then corresponds to the ground for example, strip lines or any signals that you might be routing around internal layers. So I have some examples on screen that we're going to take a look at. These example projects I have shown on the Altium Academy channel in the past. Also, these example projects are available for viewing and download on my company website. So make sure to check out the links in the description to get access to these project files. Let's go ahead and take a look. So the first project that we're going to look at is the USB to UART bridge project that I showed on Altium Academy. And again, if you want the design files for this, take a look at the links in the description. Now you can see here why this is considered a coplanar configuration, because if I zoom in here on these USB lines on the top layer, and I just go ahead and put this into single layer mode, you can see here that we have the USB lines and then we have ground on the top and the bottom placed as copper pour around these USB lines. Now, if you go to the bottom layer, we also have what could be considered coplanar ground, because you can see here we do have a VDD line in this bottom layer, but of course we also then have some coplanar ground around it. So we do have these differential pairs routing over a tiny split here between VDD and the ground region, but of course that's not going to be a huge issue because we have so much coplanar ground around these differential pairs routing over to this USB port. So this should pretty easily explain why we would call this a coplanar configuration. We have the ground in the same plane as our signal lines. So that's a pretty simple explanation. Now, the reason we have the ground in the same plane as these differential pairs is because if you watch the video about this design, which I will link in the description, we actually need the ground around these differential pairs in order to get these traces down to a small enough width in order for them to route into the pins on this component. So we kind of have to do this type of configuration. The other reason we have to do this type of configuration is because this is a two-layer board. You can see here if I swap between my layers, we only have two layers here. And so because we have two layers, we have to put the ground somewhere. And so the easiest thing to do in this type of design is to do coplanar ground, as you see here. Let's take a look at a little bit more of an advanced design, which is on 4 layers instead of 2 layers. Here we have our power module project, which again, I also showed on the Altium Academy channel. Check out the link in the description to learn more about this design. This power module or power amplifier module uses a coplanar configuration as well, but we already have a ground plane here on layer 2. And then we also have ground here on layer 3, and then we have some additional polygons on layer 4, also with coplanar ground. So because we have a ground plane here on layer 2, normally we wouldn't also have coplanar ground up on the top layer. But there's a reason we did it in this design. That is because in this design, we have a power amplifier, and that power amplifier is outputting a 6 gigahertz signal along this line. And that 6 gigahertz signal is then being routed over to a connector. So we put this into a coplanar waveguide. And in order to create a coplanar waveguide, we have to have copper pour up on the top layer. At minimum, we would need to have the coplanar ground here in this region for the coplanar waveguide. However, I've decided to put it everywhere because we also have the RF line in other locations on this design. And so that provides a lot of shielding. It allows us to put the via stitching around those lines. And by using that coplanar ground and the via stitching, we can form that coplanar waveguide and help confine that 6 gigahertz signal along this line coming from the oscillator and then this line coming from the power amplifier. Now, if you put this design into 3D, you can see where some of that coplanar ground is located. You can see it's right here in this region where we have the solder mask pulled back and the solder mask pulled off of this signal line. And then it's also here in this region where we've pulled the solder mask back from this output from our oscillator coming into our amplifier. Now, in order to balance out the copper in the stack up from the top side to the bottom side, if I put the coplanar ground on the top layer, I also want to put it here on the bottom layer. So that's why we also have the coplanar ground down here on layer 4. So if you want to reuse this project, again, go check out the links in the description. You can access the project files for free. So now, because we're dealing with defined impedance lines or controlled impedance lines, whether they're differential or single-ended, it is important to understand what determines the impedance of this line when you have the coplanar ground. Normally, if you look at an impedance solver or you look at impedance calculators, they actually don't show coplanar lines. What they show are microstrips or strip lines, just really simple lines, okay, where you don't have the coplanar ground, okay? So it only becomes a coplanar line when you bring that ground port very close to the signal line, as you can see here in the power amplifier module that we have on screen. So let's go ahead and jump onto the whiteboard and we can learn a little bit more about what defines the impedance of these lines. And then we'll look at some solutions in Polar that show what kind of S parameters we can expect from these designs. So now what I want to do is look briefly at what factors affect the impedance of a transmission line when you start to bring coplanar grounded copper poor near that transmission line. So when you have a transmission line, I'm just drawing it out like this, and let's say the width here is W. There's going to be also some thickness of the substrate beneath this transmission line. Now, the characteristic impedance of this transmission line is very simple. This is just the self-inductance divided by the self-capacitance of this line. Okay, so this is the lossless impedance. Now, the reason I'm writing out the lossless impedance is because once we look on Polar instrument software, they start from the lossless impedance and then use that to add in the losses to then give you a lossy calculation. We're going to start with the lossless impedance. So here, when we have this characteristic impedance, right, again, it's just Z0 equals square root of L over C. Now, what happens if we were to then bring in some copper poor nearby to this transmission line? And we're just going to assume this is symmetric. And we have some spacing value here, which we'll call S. Well, as we bring in this grounded copper poor, we're adding in some capacitance here, which we'll call CP. Now, this capacitance is modeled as being in parallel with the trace's self-capacitance. And so we're basically adding in some CP down here. So this is very simple. If all we did was keep the width constant and the thickness of the dielectric constant, and then we start to bring in this grounded copper poor, we're now adding in this parasitic capacitance. And so since we made this denominator larger, we now just reduced the characteristic impedance of this line. And so in order to compensate for that, what do? Well, we would then have to make this line just a little bit thinner. We'll call this W2. So when we make this line a little bit thinner, we then increase the inductance, we reduce the capacitance a little bit here, and then that restores the characteristic impedance of the line back to our target, which is normally 50 ohms. Now, what if we had a differential pair? Now, you can use grounded copper poor in a coplanar configuration around a differential pair if you want. We saw the example on the screen with the USB lines. So in that case, let's just suppose we have two traces here, and these traces are part of a differential pair. The traces have a width of W, and then there's some separation between them, which we'll call D. And then we have our separation to our grounded coplanar copper poor, which we'll call S. So normally, without the coplanar poor at all, the differential impedance of this line is 2 times this square root term, where we have the mutual inductance between these two traces, and then the mutual capacitance between these two traces. So this term is the odd impedance, and then we multiply that by 2 to get the differential impedance. Suppose we bring in this grounded copper poor close to the traces in this differential pair. What happens? Well, in this case, again, we're adding in some capacitance right here between these two lines. And that capacitance, parasitic capacitance, we'll call C sub P. And so since we're adding this in, again, it just appears here in the denominator. So what does that do? Well, it reduces the odd mode impedance of each of these traces. And by reducing the odd mode impedance of each of these traces, it then also reduces the differential impedance. How do we compensate for this? Well, we then have to change the width or change the distance between the traces in our pairs. Normally what we would do is we would make the width just a little bit smaller, and by doing that we could then restore the odd mode impedance to the target value that gives us our target differential impedance. So again, if all you did was take a single-ended transmission line or a differential transmission line, and then as it sits, bring copper pour in too close, you're gonna start to reduce the impedance of that line. And if you reduce it too much, you could then create too much return loss on that line. So to examine this a little bit deeper, let's hop into Altium Designer and hop into Polar, and let's take a deeper look at what happens when we add in grounded coplanar copper pour. So now that we know the factors contributing to the impedance of coplanar lines, let's take a look at some example calculations. First, we're gonna look at an example calculation in Altium Designer. And what I wanna do is consider a situation like this, where we have a single-ended line on, let's say, a 4-layer board, or it could be a 2-layer board. Regardless, you have ground nearby this line, and then we're gonna calculate the impedance and see what happens when we start to bring that ground in closer. So here I have a blank board, and in this blank board, as I usually do, I've just set up a basic stack up, and we're just gonna pick a decay and a thickness value for this dielectric, and then we're gonna see what happens to the impedance. So I'm gonna consider, just for fun, let's say a 5 mil dielectric, and then a decay value of 4. So pretty typical for thin dielectrics. If we look at the impedance tab here, we can add an impedance profile. And what we want to do is figure out what happens when we start to bring in that coplanar ground closer and closer to that line. And let's see if we were correct in our understanding of the formulas that determine impedance for a coplanar line. So you can see here on screen, I've calculated the width for a 50 ohm line on a DK4 substrate. And you can see here that the width is 8.968 mils, okay? Pretty simple. So to compare, we can add in another impedance profile. We're going to define this as a single coplanar impedance profile. And we can now see what happens when we bring in some coplanar ground with a specific clearance. So here, by default, the clearance is set to 5 mils. And you can see when the clearance is set to 5 mils that the width required to hit this 50 ohm target impedance is now 7.455 mils, okay? So you require a smaller impedance in order to reach that same target impedance, or a smaller width, I should say, to reach that same target impedance. Now, what would happen if we use the width that we calculated earlier, this 8.968 mil value? What would happen if we used that same width in the coplanar configuration? Well, if I take that number and I put it in here for the width in my coplanar line, you'll see here that the impedance is actually not 50 ohms, it's actually 45.73 ohms, okay? So when you start to bring in that coplanar ground near a microstrip, you now have a problem in that it lowers the impedance of the microstrip, and you compensate for that by making the width of that microstrip smaller. So now let's take a look what happens in these different situations when we use Polar to calculate the impedance and the S parameters. So here I have Polar SI9000 open. Here I have a surface microstrip that I'm going to use, and I've replicated the substrate thickness and the dielectric constant here. And you can see here if I put in that same value for the trace width, and then I replicate that up to the upper trace width and calculate the impedance, you can see here that Polar tells us that the impedance value is 50.95, or basically 51 ohms. So that's pretty good. So now let's take a look at what happens with the S parameters. Here, if we go ahead and calculate this up to, let's go up to 30 gigahertz. You can see here what the S parameters look like. Pretty good. So this is a pretty good match to a 50 ohm reference impedance, or 50 ohm target impedance. You can see here that we have very low return loss, below negative 30 dB. That would be pretty acceptable for pretty much any high frequency line that you wanted to use in the design. Now, let's take a look at this microstrip line that we just designed. But let's bring in that surface coplanar ground 5 mils away from this microstrip line, and let's see what happens to the impedance and the S parameters. So here, I'm just going to copy the width values. I'm going to go ahead and look for a coplanar microstrip here in this list. You can see here that they have a lot of stuff here. Here's our surface coplanar line with ground, and we're just going to plug in all those same parameters. We're going to use the same 5 mils for our dielectric thickness. We're going to use a DK4 for the substrate. And now we're going to plug in a ground strip separation of 5 mils. So that's the situation we examined in Altium Designer. And let's see what happens to the impedance. If I plug in this 5 mil value for the ground strip separation and I hit calculate, you can see here that we get the lower impedance just like we expect, okay? So this is replicating the result that we saw in Altium Designer. And now if we go over to the frequency dependent calculation and calculate the S parameters again out to 30 gigahertz and hit calculate, you can see here that we get significantly higher return loss. We get about 10 dB higher return loss, okay? So that's the impact of bringing in that ground closer to that line. It's gonna give you more return loss because you get bigger impedance mismatch between the transmission line impedance and, in this case, the target reference impedance of 50 ohms. And now if we just go back and let's say we use that thinner line value that we calculated for the coplanar line here at a target of 50 ohms, and we calculate that width, that's a 7.455 mils width. So if we put in that 7.455 value here for our coplanar waveguide, we do the same thing over here and we maintain that same 5 mil ground strip separation, hit calculate. You can see here that we get back to roughly the target impedance that it calculated in Altium Designer. And then here in our frequency dependent calculation, if we hit calculate for the S parameters, we get a little bit better return loss. We're now down around about negative 30 dB instead of up at about negative 25 dB. So this shows you why it's so important to accurately calculate that width value in a coplanar line. If you get it wrong, even by about a mil, you could have a pretty substantial effect on the return loss. So that's why you need a tool like Polar or like Symbior or some of the other impedance solvers that are out there. You can even use something like OpenEMS to do this calculation as well. So we'll talk about more of those tools in a future video, but for now, make sure you understand the difference between coplanar and non-coplanar waveguides, specifically as they relate to the ground strip separation between the coplanar ground and the signal line. Thanks for watching this video, everybody. Of course, I love getting your comments and questions, and if you have any kind of question that you'd like to see turned into a video, make sure to let me know on one of my videos, or of course, you can watch all of my content on Altium Academy. Make sure to subscribe to this channel, go over and subscribe to Altium Academy, and we'll see you next time.